I had the opportunity this week to speak at BMW in Munich about smart cities, connected and autonomous vehicles, and how Apache Kafka can be leveraged to integrate the multitude of data sources from these different environments and allow both the cities and the automobile manufacturers to provide new services, better quality of service, improve safety, and even enable autonomous vehicles into the future. So if this sounds interesting to you, I'd like to jump right to the talk and hope you enjoy it. So, as I was saying, a bit about myself, coming out of the world of network management, but I realized about 4 or 5 years ago that there was kind of this shift happening in the world, especially with a lot of the customers I was working with moving to these open data platforms. And as I kind of transitioned into that space, into those technologies, started doing more work around data engineering, data architecture, and ultimately realized that some of the big challenges that you had were not necessarily in what you did with the data once you had it, but all this work was the work of getting the data, getting it transformed, getting it in a usable form. How many of y'all do machine learning, AI type stuff? You ever hear those stats where they say, like, you know, data scientists spend 70% of their time just kind of getting the data into a form that they can actually use it, right? Is that true, I would assume? Right? I kind of had that similar type experience. And ultimately, that was what directed me or kind of led me toward leveraging Kafka in the projects I was working with. And that kind of brought me to this whole area of smart cities and connected vehicles, really just because someone knew I did data. And so I kind of got invited to this project, and it was really kind of interesting. In fact, I found all kinds of interesting things, how traffic kind of relates to networks. So if you think of like, cars are like packets and roads are like wires. There's some real similarities there, and things like handling queues and how do you buffer stuff and things of that nature. So there's only one thing that's kind of different, and that's that when you have congestion on a network, it just dumps packets, right? When you have congestion on the road, sometimes, unfortunately, it doesn't just dump cars. I know I've had people in front of me before. I really just wanted to dump them right off the road and drop that packet, but it didn't quite work. So let's get to what we're talking about. Came here today to talk about smart cities, going to touch on connected vehicles, going to also talk about the challenges, because I think is everyone, you know, it's obvious, I believe when you look around, there's this big move toward everything being more connected. What is connected vehicles going to bring with it? What is self-driving vehicles going to bring with it? And there's a whole lot of challenges that we all here that are involved in that have to deal with if we're going to be successful in this space. And the first is, though, we have to understand the goals. Now, if I was to take a survey of the room and I was to say, what is your number one goal that the cities should better do with their data? Probably what I would expect to hear is, we got to do something about this traffic, right? That's usually the number one. I know that's always my big pain point, right? But the reality is, for most cities, it's actually something different. It's more about safety. That's pedestrian safety is a big thing. Also, though, vehicle safety, or you could think of it as passenger safety. So the safety of the people that are actually in the vehicles. And then when it's necessary, how could we better or more proactively engage first responders, send an ambulance, send someone to address the situation when there's accidents? Is that something that could be done? Another thing, though, is reduce traffic congestion. I mean, it's not number one priority, but it is something that can be done. And then, as we look to the future, enabling connected vehicles, which also relates a lot to safety, and I'll touch on some of those points, but also how do we better also enable autonomous vehicles, which brings its own challenges with it as well. There's a lot of data out there. One of the more interesting things I realized when I got into this project I was working on is, you know, if I would just drive through the city on any given day, I'd just be thinking about where I'm going and what's the quickest way to get there. And once you get into one of these projects, it's kind of interesting because then you start to see everything with a completely different, you're seeing, oh, there's data, and oh, I see that camera there, and I wonder what that gray box on the side of the road has in it, right? And there's all these things that you realize that are out there that are just other sources of information and things that could maybe be leveraged in some way to extract greater value and make people's lives a little bit easier and a little bit safer. And so there's lots of types of data out there. So we worked with, in the project I was working on, we worked a lot with traffic cameras. So this is using computer vision to analyze the flow of traffic to detect things like the number of vehicles, how fast they're driving, the time then between observations, so you could determine something called a headway. Headway is the distance and time between the vehicles. From that, with speed, now we can figure out the actual physical distance between vehicles, then how big were they, just trying to understand all those flows. Then LiDAR, so part of this particular project, LiDAR is like radar, and they tried to get a 3D picture of things of objects that are in the view of the LiDAR. There's actually, was part of that project in Tampa, Florida, there's a sidewalk or a crosswalk. Apparently you come off of the interstate, get off the exit ramp, and it dumps you straight into a crosswalk that happens to be across from the courthouse, which is one of the most used ones. So it was like one of the most dangerous crosswalks in the state of Florida. And so what you do there is you have LiDAR that sits at that crosswalk and detects people, and then sends a notification can be sent out to the connected vehicles to say, hey, someone's coming, right? So other types of data, traffic signals. Now I would think, how many states do you think a traffic signal has? Who has a guess? Anybody? Come on. How many states does a traffic signal have? What? 20 I heard? That's a lot. That's like, most people say 3, it's red, green, and yellow. No, there's states like gap in the flow, clear the intersection, transition to green, right? There's all these like between they call phases. We'll talk about those in a little bit more detail soon. And then all kinds of other sensors, pressure sensors, induction sensors. So basically what I'm saying here, lots of different data. There's lots of sources available. There are challenges with getting to some of this data. But ultimately the goal that any smart city project is going to have, or connected vehicle project is going to have, is how do we get the right data at the right time, and that's a really critical point, especially in the connected vehicles, to the right people, processes, and things that need to leverage it, right? And I would even say, I probably should change this slide because I don't think the word data is the right word to use there, but rather the right information or insights is the correct word that I would want to use there. Okay, so let's dig into each of these individually, and I want to start talking about the right data. So in this context, the right data to me means 3 things. It means normalized, it means enriched, and it means analyzed. So it's not just raw, but rather it's transformed into some form that's going to provide greater insights. And so there's a lot of challenges with actually getting this data and working with it. So this particular picture, this is a dump out of this particular software I talked about that written by a company in the US called Metrotech. And it's a really slick computer vision thing because it has to be very high performance because you don't always have a lot of compute power out at the edge on the side of the road reading these camera feeds. It needs to be really high performance, but at the same time, do a good job of actually figuring stuff out. And I actually thought it did a fairly good job of doing that. However, there's always weird things that could happen. To start with, if we're going to do some computer vision around recognizing cars, right? The first issue we have is that this is in daylight, right? But we have a 24-hour clock, and half the day it's dark, half the day, or part of the day is dark, part's light, and you have these transitions in between, and shadows change lengths, and they change angles, and then it's raining, but it's not raining, and then a garbage bag just gets blown by the wind in front of the camera, and who knows what that was? And then you got these pesky humans, right? So here, like 91 miles per hour. Why did the computer vision, and it's this bus, by the way, the length of the vehicle, 53 feet, that's this bus here, but this knucklehead, I don't know what he's doing, but he confused the computer vision somehow to believe that when this light turns green, that bus is going to instantaneously accelerate to 91 miles an hour and zip through that intersection. So while most of this data is really outstanding, and I do think this solution does a great job, by itself, it's not good enough, right? However, as I mentioned, we have lots of other sources of information here. We have inductive sensors in the road. There might be different types of pressure sensors. There could a lot of different other things that could be leveraged to also get a perspective about what's happening at this intersection. And I think that's a key, so that was a key challenge, is that while you have sources of data, they all have a little bit different perspective. And because of various things that are just outside of your control in these type of environments, you can't always 100% depend on any one of them to be the perfect source of truth at any given time. So what do? You have to get all of these sources of data together and you normalize them and you transform them into some common semantics so that you can then have a little bit of confidence evaluation and then pick the one that might be the best one for you, right? So in this case, we would want to throw out this outlier and maybe get the speed from one of the other sensors that we have available to us. This is one of the situations where Kafka became pretty interesting for us right away, because we knew that we could always collect the data and dump it into a database or into some other thing, right? But what we really needed to do is we needed to be able to collect that data and transform it and work with it in between. So it was about more than just pure collection. It was about being able to collect it and then have mechanisms to normalize, ultimately with the goal of having a topic, right? A topic, I know this is the Kafka meetup, but I don't want to throw out terms that not everyone's familiar with, right? So a topic being a instance of a commit log of a stream of data inside of Kafka. So we could get that data into a topic and have a clean, normalized topic that may be fed from multiple sources and is completely decoupled from what we're going to do with that data for further analytics down the road, right? So to get data into Kafka, though, there's a number of different things you have available. These things that send data into Kafka called producers, and you got a number of ways to do that. One thing is called Kafka Connect, which is a platform that allows you to develop connectors on top of that can also be distributed in a scalable, highly available manner, just like Kafka, and use it to, one, get data into Kafka, and as we'll talk about later, also take data back out of Kafka. But there's also client libraries. In this particular case, we ended up using, was that one? I believe that one was the JavaScript library, or a JavaScript library. There are a bunch of libraries that are managed by or developed and maintained by Confluent itself. There's also libraries that are handled by the community. JavaScript library was one of those. And the way this can kind of look in real life, so this is what we ended up with. Metrotech happened to have a box, they called it the IntelliSection, where they could run some software out on the edge, as well as Cisco Kinetic devices, because some of the cities we were working with had a relationship with Cisco. They actually use different technologies. One of those is a thing called Iot Dsa. Now, I've found that Iot Dsa is not very well known actually here in Europe for some reason. Anyone ever heard of that before? Yeah, it kind of has some relation to MQTT, but uses a multi-broker thing, and you create these DS links, they're called, to interconnect things with each other, to have them talk to each other. And it's the foundation, Cisco Kinetic uses that as a foundation for its communications. And so what happens is you can have applications that run in containers that can actually run on a Cisco Kinetic device or on this Metrotech IntelliSection device. And so the IntelliSection we built, because this was basically our code. So we built compatibility for that, as well as Azure's IoT Edge was in use. So that was like when IoT Edge was in preview. The developer that was working on that, really, it was a stressful thing. The end product ended up being pretty good. I think we ended up rewriting that like 6 times because the library would keep changing and changing and changing. But in the end, it was pretty good. And so we went over Iot Dsa and then ultimately used a connector. Now this particular connector is out of the community. It's managed by the Iot Dsa project itself and could then send the data into Kafka. And we also had the IoT Edge stuff, went to IoT Hub, where we then used a Microsoft developed connector that is also available. You can, if you go into Confluent Hub, which is where Confluent maintains a lot of their own or makes available a lot of their own and other partner connectors, you can, this connector is available there as well. And so Microsoft connector to talk to IoT Hub and push data into Kafka. Just a quick interruption to say that if you're getting some value from this video, please hit the like button below. And if you're interested in content like this in the future, hit the subscribe button so that you can follow the channel. Once you have it in, you got to do something with it. You got to transform it. You got to make it usable. And that brings up the other challenge that you have in smart cities is if you think about I'm sure some of you may have occasionally noticed walking down the road like some gray metal box on the side of the road. Sometimes they bury some of that stuff in the ground, but I mean, the Europeans tend to bury it in the ground. Americans, we love to just like stick it up in an ugly pole with wires hanging all over the place. But inside of those boxes, you got all these devices. Now, they don't have very large compute power. So there's a lot of challenge, not lots of bandwidth. And so they tend to heavily encode. This is another thing I was familiar with from my time in networking, is you tend to encode data into very compact structures. So in this particular case, this is what's called ATSPM data. Basically, it's traffic signal data. So it's communication of the lights and all the different signal indicators on an intersection. Can the pedestrian walk? Can he not walk? Is the light green? Are we transitioning to a yellow, et cetera? And that's actually, so we get a timestamp, and then we get this little code here, which is the sensor ID. So this is 80, and then we have all these little phases here, right? So the second one is a phase of this. And based on what that number is, we can't even know what the last number is until we understand what the next to last number is. So, and of course, I don't care who the traffic engineer is, I'd be surprised to see anyone who remembers all of these, right? So you obviously have to do some serious enrichment of this data to really make it, to be able to be processed by machines down the road. So this particular example, I happened to pull out because of this here, right? So we talked about those different phases. Who said 20 before? Yeah, I don't know the exact number, but it's a lot, but there's definitely a lot of them. So here's one of them, gap out. So gap out is when the sensors in the road, they've detected that the light's green, and they've detected it's been a while since I've seen a car. So things are probably thinning out. We haven't really hit our timeout yet to go red, but because we haven't seen a car, you know, it's been a little bit of time, which a little bit of time might mean a second and a half, right? It's not a long period of time. Let's go ahead and transition out of this green phase, right? So right after a gap out, we get a green termination, then we get a begin yellow clearance. So let me ask you a question. How many of you ever been at a light and the lights went green, right? And 3 cars go, 4 cars go, but that guy in front of you is messing with his radio or phone or who knows what he's doing, and you're like, honk, go. He's like, hits the gas and takes off, and now finally you can go, and the light goes yellow, right? Right? You've just been gapped out, right? That's what happened. He just gapped you out, and you're stuck at red. That's about that moment where you're thinking, can we really not drop packets here? I'd love to just like kick this guy right off the road, right? A lot of data has to have a lot of enrichment that happens to make it useful. And so that's again where kind of Kafka came to the rescue a bit. So once we had the raw data inside of Kafka, we needed some ability to transform it, manipulate it, do additional things with it. And there's 2 features that you can take advantage of. They're really related. One of them is Kafka has the Streams API. So the Streams API is you can use Java or Scala to write Streams applications that can be scaled up and down as needed and that act on data for the topics you develop them for, right? Configure them to work with, and can do things like transformations. You could do various types of analysis. Pretty much, I mean, it's Java or Scala code. So it can, in theory, do whatever you dream it needs to do, and then outputs those results back onto another topic, right? Or if you're not a Java or Scala programmer and you have a pretty simple use case and you think, man, is there not an easier way? Actually, yes, there is. It's called KSQL. And KSQL allows you to use a SQL-like syntax to write something this is just an example here of something, right? Where you can do things like windowing and calculate averages of things and do different transformations of data to also do streams processing of that raw data and put it in some state and turn it into some type of information that's of value to you, right? So 2 things that you could leverage. Here's another example where we took the camera feed, we put it in a topic, observation raw. So this is our raw data, unenriched, unnormalized, and we'd use some KSQL to do a geo-lat-long enrichment. So ultimately this data is going to end up, this here is an Elasticsearch dashboard or a Kibana dashboard. So we're putting our data in Elasticsearch because in this particular use case, we needed to do some geo-related analysis, and Elasticsearch gave us GeoPoint, GeoShape type query capability. we got the data from the different cities that we were working with, put that data also into Kafka, and then use KSQL to enrich the raw messages we were getting on this raw topic, adding the lat long information to it. And now we write it in this metadata topic. The next thing we wanted to do then is begin to analyze that data. And so we would send that data to Kafka streams because we wanted to do further analysis of it. So with streams, we have now a whole lot more flexibility available to us. And so we wrote streams applications that would leverage or access some models that were calculated with some machine learning algorithms. The machine learning stuff was in Python, but then we took the models out and could leverage the models and some Scala code actually in this case. And we came up with these things called health score, like a relevant health score. There was an absolute health score and a relevant health score, right? It says, why is that important? Because again, thinking on the end user, how many of you know already, right, that on Monday at 8 in the morning, traffic's horrible, if it's not a holiday, right? I don't need any machine learning to tell me that, right? But what is relevant to me is it less horrible or more horrible than it usually is, right? That's useful information, and that's that absolute versus relative. And also to do incident detection, okay? So what we want to do with incident detection is be able to look at the speed of traffic, the normal flow, the normal headway, the space between vehicles, and try to determine or infer if an accident has occurred. Because if we can infer an accident's occurred, send an alert to like a traffic operator, someone that's working in traffic operations, who could then just bring up the camera and look, go, yep, sure enough, accident, and could actually be on the phone to, I want to say 911, but I know in Germany it's not 911, and I really should know what the emergency number is. What is it? 112. Okay. What's 114? Is there a 114 too? I don't know what's in my head. Anyway, 112. Okay, 112. So, and can dispatch those emergency personnel before people have even realized what's happened, got out of their days and called somebody, right? So, so that was a pretty important feature that the cities that we were talking to were really interested in. Now, here's where it gets challenging, right? Is like, let's take that measurement headway. So, and again, that's that time between you and the vehicle ahead of you. Well, at say 100 kilometers an hour, 1 second is a long way away, right? But at 10 kilometers an hour, 1 second is like right on the rear end of the car in front of you, right? So it's relevant. So think about also a traffic light, right? What's 1 second when it just turned from red to green is completely different than 1 second of headway when the light's been green already for 15 or 20 seconds. So now you get into this thing where, we have that signaling information we had before, and now we have to bring the signaling information into the analytics to figure out, make all of our analytics phase specific, and you get into some really interesting stuff that can happen. But again, you see, you cannot do this with one data source alone. You have to have these multiple sources of data that you're bringing in and leveraging them together to get a complete picture of what's happening. And then I said again, finally, stuff in Elasticsearch. Here was a city in the US that gets it, no big surprise. Santa Clara County, Silicon Valley, California. The roads themselves are colored with data coming from Bing's real-time traffic feed. And you add to that these little circles. So each of these has cameras at multiple places in the intersection, and they're at the moment showing the relative traffic. And it's trying to give this extra perspective, okay? So we have multiple feeds showing up on one thing so that a traffic operator can get a better understanding. So just an example. But it was really on this project for the first time where I realized, this is kind of serious stuff, right? I mean, these are potentially life and death type things. And so when I say the right time, when I talk about the right data or insights at the right time to the right people and processes, what I'm talking about increasingly is real time. Right? And so increasingly at the right time, and that's just not in this use case, but increasingly it's real time. So I have one very concrete example that I want to talk about. Anyone happen to know what this is a picture of, this car? Specifically this car?
First kill of the pedestrian by autonomous car.
Exactly, right? Arizona in the US, Uber self-driving car struck and killed a woman crossing the street with her bicycle. It was big news, I think about 2 years ago now, maybe a little more than that. So the analysis was done, and what the analysis of that accident came up with is they said somewhere a little over 5 seconds before impact, right? The car said, I see something. Don't know what it is, but I see something, right? Then it just over is like 1.1, 1.2, like just over 1 second from impact, it said, oh, that's a bicycle. And actually, if you look closely, there's an orange line which indicates the middle of the lane, and the green line which indicates the middle of the path the vehicle took. So you could see that it did start to go away from, try to veer away from the driver. Now, it's estimated, apparently the speed limit was about 35 miles per hour, so what's that, about 50 kilometers an hour? And it's estimated the car was probably traveling actually about 70 kilometers an hour. And at the time it started to make its break away, it was less than 20 meters, right? So just wasn't enough time. And so I increasingly believe that that's the real challenge. That's what I mean about real time, right? Because if that vehicle could have identified earlier that there was something there or had another piece of information, because it knew it saw something, but it just couldn't make a quick enough determination to then decide that it actually needed to take an action. So this is what we mean when we're talking real time in these use cases. And so, so the challenge is, right, a autonomous vehicle, it's limited, as much work as they put into it, it's still limited by the sensors that it has on the vehicle. It's line of sight. So it can't see around a corner. It can't see over a hill. It only has that line of sight of the sensors that it has. So what if, though, we could say, for example, let this car's perception phase, there's multiple phases that have to do with the way an autonomous vehicle works, and one of them is called perception. And perception is basically all the data feeds, all the inputs where it then perceives its reality around it. So what if we could take the perception of this vehicle, who clearly can see around this corner, and we could provide that information to this vehicle, or something over a hill, right? Or maybe just some LiDAR that's sitting on the sidewalk and knows where all the pedestrians are. So you're constantly streaming and feeding out in kind of like a peer-to-peer manner that information to the other connected cars. So now, literally, the connected car, there might be 3 hills and 2 curves, and I still know that, 500 meters down the Autobahn, a deer ran across the road, right? Because some other car saw it and could just give me that information. So I think ultimately that's where we're going to go, and that's where this cooperation, really through 3 entities, right? One of those entities would be obviously the cars themselves, but also the cities that have a lot of data that could be leveraged and be made available. And also the network providers are going to have to play a role here. I really do think that's where 5G is going to be a big use case for 5G, is because you have a lot of small antennas spaced really close together, and so you have a better connectivity foundation through which you can do types of peer-to-peer stuff. But we still have to, for example, figure out how we're going to take a single stream or a feed from one of these vehicles and from its sensors, and then split that out to multiple vehicles that are within that particular geographic area for which that data might be relevant. And so all the things I talked about earlier were really about taking data and bringing that data in to some central type cluster where you could do all this analysis and stuff. And now that can be pretty high performing. In fact, we found that when we had a vehicle's observation to it showing up on our dashboards, we're usually talking about 3 to 4 seconds max that we could make that happen, right? That's going from the edge to our cloud edge, through our Kafka cluster, through our streams analysis, into Elasticsearch, and when the dashboard refreshes, show it up on a dashboard. But in these use cases, even that's just too much time, right? That particular architecture would not have save that woman's life, right? But if we could take these brokers and we could push them out to the edge. So in other words, we still have all the advantages of our centralized cluster, but we could geographically disperse our cluster out and have brokers that are also out on the edge that are also working together in one big virtual environment. That would be really great. And we really didn't have that option, but Confluent has come out with Confluent Platform 5.4, a brand new feature, multi-region clusters. Now, this particular feature has different use cases, right? Some of it is like maybe DR, or maybe I just have multiple data centers, they're geographically dispersed, and I want to have a cluster that spreads across those without having to worry about the issues of network latency and things of that nature. However, it's also a feature that is going to allow these type of use cases that I just talked about to be addressed. So everything I told you before, that's stuff that's built and proven. We did it in this project in the US. And this here, I think, is going to go with that next step, where we're going to see cities and cars talking to each other, and with Kafka kind of supporting the whole thing. Again, write data. I'm going to say write information and insights. I'm changing this slide when I get done. Write information and insights at the right time, increasingly real time, to the right people, processes, and systems. And that's why Kafka became the nervous system that was central to the platform that we ended up building. So I hope you enjoyed the video. If you got some value out of it, again, please hit the like button. And if you're interested in content like this in the future, go ahead and hit subscribe and follow along on the channel. Thanks, and until next time.